Okay, hello, you all. So today I want to talk more about the reproductive number, this number which tells us something about which summarizes how contagious a disease is, and tells us something about how the course of an epidemic will go. I hope you've all watched the Johns Hopkins video that I posted. So it's a follow-up to that, and I will talk more about the question that I asked you at the end of that one on the form. So let me bring up our slides. So we're going to be talking about these reproductive numbers, R naught and R, and about the idea of herd immunity. So quick review of the definitions. R naught is a basic reproductive number. That is a number that describes how many people will be infected by one person who shows up with the disease in a population that's completely vulnerable, that has no immunities to the disease. I should emphasize that R naught is an average. For many diseases, you may well have many people who get sick and don't infect anyone, and a few people who get sick and due to what we call super spreading events might infect a large number of people. Then R naught would be the average of those smaller and larger numbers. And again, this is the average in a population with no immunities. One of the more extreme examples of this in history is when the Spanish colonists showed up, colonizers in the Americas, and spread smallpox like wildfire through a population that had no immunities to it at that point. So that's R naught. Then there's also R, which is also sometimes called RE, the effective reproductive number. And that describes what's going on sometime into an epidemic. As an outbreak has been happening, R describes the average number of people that one infected person will spread the disease to at that point, and it changes over time. So that's my first question for you to answer on the form. What is it that affects R? Why does R get smaller over time, even though R naught doesn't change? So give me your thoughts on that. I want to show you a couple of pictures. This shows what would happen with an epidemic for a disease with an R naught of 3. We have this index case, this first person who infects 3 people. Each of those 3 people in turn infects 3 people, and you're going to get exponential growth, 3 times as many people in each generation. But that won't keep happening forever. In most diseases, once you've had them and recovered, you are then immune to them for at least some period of time. So over here, this picture represents what happens sometime into the epidemic, where these white cases, these white circles, are people who have had the disease and are now immune. So now somebody gets sick, and just like our index case over here, they come into contact and would spread the disease to 3 people, but 2 of those people are immune to it. So it basically bounces off of them. So they only spread the disease to 1 person. And that one person in turn would spread it to 3 people if there were no immunities, but there are, so they only spread it to 1 person. So this is a picture of an R of 1, an endemic disease where each person spreads the disease to 1 more person, and then the original person presumably gets better. And so the amount of the disease in the population doesn't change. We don't have an outbreak. It doesn't die out either. In infectious diseases, we often talk about what were called childhood diseases like mumps and measles and polio. And so people have asked me, why children? Why do we talk about polio? Why are they surveilling children in Afghanistan and Pakistan these days for polio? Why not everybody? And the answer is because generally, when there are serious infectious diseases in the population, by the time you get to be an adult, you have probably gone through such an epidemic, or more than one, and gotten some immunities to it. So you have a population where everybody has some immunities, the disease isn't going to get a foothold. But children are being born, and those children are not immune. So over time, you will have a growing population of children who have not lived through an outbreak. And then that group will get large enough that the disease will show up in this population, and it will spread in an epidemic-like fashion through the children. until they get their immunities. So we think of these as being childhood diseases because people developed immunities by the time they lived to be adults. Here's a graph of here's a picture showing the progress, a very simplified progress of two different epidemics with two different R naught values. This first one is an R naught of 1.5. The second one is a larger R naught of 2.5, and I think it's interesting to compare and contrast. We're assuming a population of 1 million people. And on these graphs, the blue line shows the number of people in the population who are susceptible to the disease. That is, have not yet had it. So initially, everybody is susceptible. The red line shows the number of people who are currently sick with the disease. And we're assuming this disease lasts for 3 days. And by the way, we're assuming it's contagious immediately. The green line shows the people who have recovered from the disease and are therefore immune. So initially, nobody is recovered, and that will be increasing over time. So what are some interesting features of this? First of all, I want you to notice the course of the disease in both of these cases. Initially, it is growing. This one down here might not look like it's growing very quickly, but you really would see that it was if we zoomed in on it. If you look at the red over here, you can see that it's growing. So it grows fairly quickly at first, and then it starts to level out. And again, this is just because the number of immunities in the population, the rate of the percentage of people who are green, who have recovered, is increasing. So when somebody gets sick, they're not infecting as many people. So it starts out growing very quickly, then it levels out, and it reaches a point where there are enough people immune that each sick person is on average infecting less than one person. So where the R value is less than 1, even though the R naught value is still 1.5. And this is the decreasing phase of the epidemic as it is slowing down. Now notice that even when the epidemic is over, when nobody is sick, there are still a reasonable number of people who never caught the disease. Over in this picture, this disease with an R naught of 1.5, we can see that almost half of the population is still susceptible. They just never caught it. They got lucky. And the other half of the population is recovered, or technically they may have died. So this outbreak will rise, will rise and fall. And when it's over, some people are still vulnerable. We see the same thing over here with this larger R naught value. Many more people would get sick with this more contagious disease, but even so, this is about 15% of the population never caught it. Almost everybody is recovered, but not all of them. So that's one thing to notice. Notice with the higher R naught value at 2.5, the peak of the epidemic, the total number of people sick at a time, is substantially higher. So that's substantially more stress on the hospital system, for example. Another interesting thing to notice is that this higher R naught epidemic goes more quickly. These are both the same basic model of a disease, that is, the disease lasts for 3 days, so the course of the disease progress should be about the same. But this one, the epidemic is over in 40 days, whereas here, 40 days in, we're at the peak of it, and it isn't over until more like 100 days. It's traveling more slowly, so the immunities are progressing through the population more slowly. So the disease lasts for longer, and that is something people were thinking about as we're all talking about flatten the curve on COVID. A high curve, a very contagious disease, will get many more people sick, much more stress on the system, many more deaths, but it would have been over faster than this slower, flatter curve that we're in the middle of. Here's some R naught values for some actual diseases. You can see measles and chickenpox, which are aerosolized. That is, they're born in incredibly small particles which can stay in the air for hours, have enormous R naught values. Measles at 12 to 18 is just incredibly contagious. One person sick with measles means everybody gets it. Then you have a bunch of diseases that are born in respiratory droplets, including the flu and COVID. Those have R naught values generally somewhere between 1 and about 5. A few born different ways: direct contact with bodily fluids like HIV, AIDS, and Ebola. HIV here has a relatively high R0 value because somebody stays contagious with it essentially for their entire life. That is unlike any of the others on here. A diphtheria, where you have to come in direct contact with somebody's saliva, and polio, which like cholera is carried through the fecal-oral route, largely carried in contaminated water. And it's worth pointing out at this point that R0 is not some absolute fact about the disease. It depends on the disease and a population. What's interesting actually is the R0 values tend to be fairly stable in our environments, except when you get into cases with worse sanitation. Cholera, for example, which is spread through contaminated water, the R0 value with good water sanitation is tiny. We basically don't see cases of cholera spreading. But when various things cause sanitation to drop, like in Haiti after the earthquake, when there was no municipal water systems and people drinking whatever water they could find, then cholera can skyrocket. And we've seen R0 values that people have estimated to be as high as the mind-boggling one sick person infecting 1,000 others. So there's this incredibly wide range. So I want to talk about the relationship between R0 and R. So R0 is a number of people that one infected person would spread the disease to at the beginning of an outbreak, whereas R0 is what would happen sometime during an outbreak. And this is assuming that we're not making any other efforts to control the epidemic. We're just letting it spread. So if half of the people, for example, are immune, then one sick person is only going to spread it to half of the number of people they otherwise would. The disease is going to bounce off half of the people they come into contact with. So in general, R is R0 times the fraction of the population that is still susceptible to the disease. And as the disease goes on, more people have had it, fewer people are susceptible, we see R dropping off. So I want you to think about this for a moment. Let's say let's say smallpox has an R0 value of 4. Then what fraction of the population would need to be immune for a smallpox epidemic to start to be decreasing instead of increasing? I want you to think about that and answer on the form. So this would happen when the R value is equal to 1, and R value is 4 times the fraction of the population still susceptible. So we need no more than 1/4 of the population to be susceptible, or for 3/4 of the population to be immune. So if 75% of the population has gotten smallpox, either in this outbreak or in previous outbreaks, if 75% of the population has immunities, then our outbreak will start to go down instead of go up. We'll be in this decreasing phase of an epidemic. And actually, it's a good opportunity for me to say, back before people understood this relationship between R0 and R, they certainly knew that when they had outbreaks of diseases like the plague or like smallpox, that they went up and then came back down again, and they didn't understand why they went down. And there were all of these ideas. Do viruses, they didn't know what viruses were, but does whatever makes this disease spread, does it somehow get less effective over time? As it spreads from person to person, does it get weaker? And a lot of people believed that was the case. And eventually they came to realize that, nope, the virus, the infectious thing, is as powerful as it ever was. It's just, as people get immune, it just can't spread as far. And honestly, I'm seeing some of this now with people speculating that COVID will somehow just magically get weaker and die off. And the sad truth is, it won't. So that's our relationship between R0 and R. So what if you have a population where 80% of the people have already had smallpox? Remember, if 75% of the people had gotten it, then your R value would be bigger than 1. So now what if we have a population where 80% of the people have already had it and a new case shows up? What's going to happen? Answer this on the form. So in that case, R would be 4 times 0.2, the percentage of the population that's still susceptible, is 0.8. There won't be an outbreak. So that one person might affect somebody else, they might not. The disease will pretty quickly just disappear. We call this herd immunity. If enough people in a population have immunities, that the effective R value for a disease is less than 1, then you won't get outbreaks. New cases will quickly die out. So we can ask how many people need to have immunities for a population to have herd immunity to a disease to prevent that disease from ever creating outbreaks. Now let's think about a population where 80% of the people have been vaccinated against smallpox and a new case is introduced. Exactly the same thing will happen. It doesn't matter whether they had it or were vaccinated against it. 80% vaccination rate is high enough that you will not get smallpox outbreaks. You need your vaccination rate to be above 75%, because 75% was that magic number where R is equal to 1. And this is an important idea. This says that vaccination doesn't just protect you, it keeps you from getting sick, but it also protects the entire population. So remember, 80% of the people vaccinated means essentially nobody will get smallpox. So those 80% who are vaccinated are protecting not just themselves, but also the other 20%. And this is important because not everybody can be vaccinated. We can't vaccinate babies until their immune systems have developed enough. We can't vaccinate people who are immune compromised. Some vaccines become less effective over time. So as people become older, they might lose that protection without knowing it. But if we vaccinate enough people, if we hit that herd immunity level, then everyone is protected. And these are some pictures showing that for flu with an R-naught value of about 1.2. Up here, you have 2 people who get the flu, and you can see it spreading through most of the population. Not quite all. A few people manage to avoid getting it, but it spreads through most people. Whereas down here, these blue people are vaccinated, and this isn't very many. In this case, it's only a 30% vaccination rate, and that's okay because it's a pretty low R-naught value. So even with this pretty low vaccination rate of 30%, you can see that our chains of transmission of the flu start running into vaccinated people, and they stop. So this flu transmission chain ended here with these vaccinated people stopping it. This one went on for a little bit longer, but again, it dribbled out. We had an R value with this vaccination rate of 30%. The R value was low enough that the flu never took off, and these 30% of people who were essentially good citizens who went out and got vaccinated protected not just themselves, but this huge crowd of yellow people who were healthy, susceptible people who just didn't get the flu because they had been protected. I'm spending time on this because I really think it's worth understanding that vaccination protects not just you, but everybody, as long as we can get those vaccination rates up high enough. And so that's our next question. How many people do we need to vaccinate? I've really talked about all the pieces that you need on here, so let's just pull them together. Let's look at chickenpox, which has an R-naught value of 10 to 12. It's pretty large. It's quite contagious, so not quite as contagious as measles. So R-naught is 10 to 12. About what percentage of the population do we need to be vaccinated to have herd immunity against chickenpox? I'd like you to try to calculate this and answer on the form. Okay? Since the R-naught value is between 10 and 12, we need something between 1/10 and 1/12, that is between 10% and 8.3%, or 8% to 3% of the population can remain unvaccinated and still get us to herd immunity. So that's 1 over R-naught is the maximum number of people who can still be susceptible if we want herd immunity. So we need to vaccinate, let's say 90 to 92% of the population. But if we can get those vaccination rates up to 92% or more, then we're not going to see chickenpox outbreaks. Now it's the same thing for the seasonal flu with an R-naught value of between 1.2 and 1.8%. And this one's a little trickier to calculate, but what percentage needs to be successfully vaccinated? And if you can figure it out, think about how you would deal with the fact that the vaccine is not 100% effective. It's only about 70% effective. And given that, then can you figure out what % of people would need to get the vaccine? Answer on the form. Oops. I just skipped a line. I will answer the seasonal flu one, but my slides are in the wrong order. I'm sorry. I want you to do the same calculation for measles. Don't worry about the success rate of the vaccine. Just assuming successful vaccination, measles has an R0 value of between 12 and 18. What percentage of the population needs to be vaccinated against measles? So answer the question for both the flu and for measles. So let's see, here are my calculations. So for the flu, the R0's pretty low, this 1.2 to 1.8. So that means we need somewhere between, where we can still have somewhere between 55% and 83% of the population still susceptible. And we can have the herd immunity that we need. 1 over 1.2 is 83%. 1 over 1.8 is 55%. So we need something between 17% and 45% of the population to be successfully vaccinated. That doesn't sound that large. That's pretty good, you know. I mean, a lot of people don't get their flu vaccine. It's not quite as good as it sounds because, as I asked you, the flu vaccine doesn't always work. It varies from year to year. They have to make guesses about what that year's flu looked like. So let's say the flu vaccine is only about 70% effective. So if it's only about 70% effective, then it turns out in order to get 20% of the people vaccinated, we would need 30% of the population to get the vaccine, because 30 times 70 is 21. And if we needed to get half the population vaccinated, we would need 70% of the population to get the vaccine, because 70% effective, 70% of the population gets you 49% of the population actually immune. So since the vaccine is not perfectly effective, we need somewhere between 30 and maybe 70% of the population to get that vaccine to get herd immunity against the flu. I believe they have typically been targeting about a 60% vaccination rate, realistically speaking, and I think they haven't gotten that for many years. So that's our calculation for the flu. For measles, if we try to do the same calculation, you'll see that we need almost everybody to be vaccinated. We need the susceptible rate to be under 10%, somewhere like 5 to 8% of the population. Since no vaccine is perfect and we can't vaccinate everybody, that means in order to get herd immunity against measles, we need virtually the entire population to be vaccinated in order to maintain that. We'd really like to get 95% of the people successfully vaccinated. So as our diseases get more contagious, we need higher and higher vaccination rates to protect people against them, to give the population herd immunity. So that's the end of this topic. Next time, sorry, I'm just trying to get Zoom to work. We'll have one more, there we go, that's what I was looking for, sorry. One more video where I'm going to talk about other ways to control an epidemic other than herd immunity, because herd immunity is great once you reach it, but getting there can be very painful. So I want to talk about some of our other prevention approaches, and in the next video I will talk fairly extensively about COVID.